This way, what we will be able to do is to see different shortest path algorithms all as instances of the same general outline for these sorts of algorithms. Okay, so let us see what is the structure of these equations, right? So there are, so here is the single source equation, which basically says that these distances are from a source vertex S, and what it says is that the shortest distance to a vertex V is obtained by first going to some vertex U and then going from U to V. Okay, the L is the length of the edge, right? So it tells you how far you have to go. So it tells you the weight of this edge, and basically what it captures is that in order to get to V, you first have to go to some neighbor of V, and then from that neighbor you need to go to V, right? So that's what this equation captures. So in that sense, this is pretty obvious, right? So you can't really have any other equation. So you don't have to, so the equation is very obvious in that sense, right? There's nothing, there is physically no way to get to a vertex V without first going to one of its neighbors, right? And notice that the neighbor could itself be S, or in fact, we will allow the neighbor to be itself. So we'll see that in the next slide. So if you want to go to consider all pairs problem, then you're taking two vertices U and V, and you're trying to get to V from U, okay? And the way you do that is, well, you have to go through some intermediate vertex. Let's call it W. And then, so therefore you end up going from U to W and then W to V, right? And you take the minimum over all possible such cases, and you end up with this equation, okay? I'm sorry, so this is, I was explaining this equation. So you go from D to W, U to W, and then from W to V. Or else, you could think in the same way that we did for this equation, which says that in order to go to V, you first have to go to one of its neighbors, right? Let's call it W. So then the shortest distance is going to be the shortest distance to W plus the length of the edge from W to V, right? So all of these are fairly easy to understand, and no one needs to sort of convince you that these are correct, right? You stare at them, you sort of know that they are correct. So now what we are going to do is that we are going to just try to set this up as a matrix equation, right? So so again, see what this says. Remember, we are doing our usual thing, which is that we do matrix multiplication, but when we expand out the matrix multiplication, we are going to treat multiplication as integer addition, and the original addition as a min operation, okay? So as we have discussed many times, when you do that formulation, it becomes essentially like the shortest path formulation, and it in fact matches exactly this first equation that we have here, right? So we want to say dV equals min of this, and if you look at, okay, let's look at D1. D1 is L11 plus D1, okay? Or L21 plus D2. That is, you go from the source vertex to D2, and then from D2 you take L21 to go to the vertex 1, right? So essentially, if you write out, say, the first line, right? So D1 on the left-hand side equals minimum of D1 plus D2, right? So we are just doing this multiplication of this row with that column. Right? So this is the distance D1, right? So we are basically saying, you need to first go to some other vertex, and then from there you go to 1 from there using one edge. Okay, so essentially, although we write this as all possible vertices, right? So we first go to D2 and then go from 2 to 1, or we go to D3, rather vertex 3, and then from the vertex 3 we go to 1, or vertex n, and from vertex n we go to 1, right? So this is what that equation is capturing. So now you see that this is why this matrix formulation is exactly saying what equation we had before. Okay? So any questions on that? Very quiet. So is it just too obvious, or okay, so even that is okay. So let's move on. So once you have this equation in this form, okay, so then we can talk about how to solve this iteratively. So we will now take this equation and write it down in this form, right? So D is the distance matrix, and L is the length matrix, right? So notice that one thing that we did in the previous slide is that we defined L UU equals 0, which basically says that we are assuming that you can always go from a vertex to itself without any cost, right? So this is useful because otherwise this equation would have to be something like dv equals min of dv comma du plus LUV, because we may already have computed the shortest path to V, so then you just pick it, or else you may have to first go to some neighbor of V and then go from there to V, right? So essentially what you're saying here is that it is possible that, so this is V, this is S, and this might be U, right? So it may be the case that the shortest path goes through U, or the shortest path may not go through U, it may just directly go to V, right? So to capture that, we have to say that it could be the minimum of the value you already have computed, or maybe there is a shorter path that goes through U, right? This is the form of the equation if you want to capture that. But in case you allow, this, if you say UU is always 0, then this possibility that you already computed the shortest path to V is already captured here by just letting U be V, and then this will be LVV, which is 0. Right? So it's just a notational trick to avoid having to write down, one more thing. Okay? So otherwise, it really doesn't make much of a difference. We can just stick to this simpler form of the equation if we made this simple notational thing that says LUU equal to 0. That is, basically you can go from a vertex to itself without paying any cost, right? Which also makes sort of logical sense, right? There is no cost to stay in the same node. Okay, so once we do this, so we have this equation, right? So D is the distance matrix, and L is the adjacency matrix of the graph, except that instead of just telling you whether it's 1 or 0, it gives you each entry in this matrix L tells you the length of that particular edge, or we also call it as the weight of that edge. Right? So you have D equals LD, and now what we are going to do is we are going to use an iterative technique to solve this. Okay? So once you have this equation, which is a recursive equation, we simply are going to use an iterative technique to solve it. And this is exactly what we'll do for all of the cases to derive all the shortest path algorithms that we are going to study in this course. So D0 is essentially our initial approximation, right? Our initial approximation is a matrix that says infinity everywhere except at the source vertex itself. Right? So if you think about how you would initialize the distance in the, say, in the Dijkstra algorithm, this is exactly what you do, right? You say that I already know a zero cost path to the source, and for everything else, I haven't computed a path, so I'm going to say I know a path of cost infinity, right? So that is my initial estimate. D1, I'm going to obtain. Remember how we do this iterative procedure. We take an initial approximation, plug it into the right-hand side, and then get the next approximation. Right? So what we are doing here is that we are going to take our initial approximation D0, and we are going to put it over here. Right? So D1 equals L times D0. Right? And D0 being Z, so that's why D1 is L times Z. Okay? Now, if you do D2, D2 is going to be L times D1, right? So we're going to substitute this approximation into the right-hand side. So D2 equals L times D1, and D1 is LZ, so we're going to substitute that. So that gives you L times Z, which is L squared Z, right? And so on. So in general, if you extend this, you will say that you'll be able to see that D, the ith approximation of D is going to be nothing but L raised to the power I, right, times Z. Okay, so again, remember that this I is not exactly a power. This is the approximation. Whereas here, this refers to a power, right, the exponent. Right, so it's on the one hand, you might wonder why I'm using exponent to mean two different things, but on the other hand, they have this natural relationship, so it's kind of has a certain appeal because these two I's kind of match, right? But really, what we mean is Di is the ith approximation for D, and Li here refers to L raised to the power I. So yeah, we have said already L is a generalized adjacency matrix where entries are correspond to edge weights rather than being just 0 or 1. Okay, so you can ignore the last point at least for now, but later on you might want to think about this. Okay, so we already have talked about matrix formulations and this form of matrix formulation and how it relates to shortest paths, right? So we know this already. That is, when we do this, in particular, what we have said is that when you do this L to the power I, that essentially captures the length of the shortest path that uses I or fewer edges, right? So, because we said that L tells you, okay, whether the cost of doing this using one, at most one edge, right? So, what is the shortest path that uses one edge? That's what L gives you. L times L, well, you have to go from, you have to use essentially. So for instance, L. If you add L12 plus L23, right, that is spelling out a path that grows from vertex 1 to 2 to 3, right? So this is your L12 cost, and that is L23 cost, right? When you add this, what you are saying is that, well, I have a path of length 2 that goes first from 1 to 2 and 2 to 3, right? So this is the sort of the term that you're going to get when you multiply L, the matrix L by itself. So essentially, L squared captures all paths of length 2, L cubed captures all paths of length 4, or at least the shortest path of length 3, and so on. So in general, if you have L to the power I, then you have a shortest path that uses I or fewer edges. Okay? So since we know that no path needs to be longer than n, right? So unless you have cycles that have a negative cost, there is no sense. You will not have any paths, shortest paths, that have more than n edges, or rather n minus 1 edges. Okay? So it's enough to go up to L to the power n, or in other words, you can stop with the nth approximation in this iterative procedure, right? So you can keep doing this until you get to say d, the nth approximation of d. At that point, you should have computed the shortest path from S to every vertex. Okay, so this is a simple iterative procedure where we just use some basic, some standard way of solving matrix equations by essentially using successive approximations. Okay, so, but unfortunately this, although we have a procedure for computing the shortest path, it's not particularly fast, right? Because if you do this matrix multiplication, that's O of n cubed, or you could use some technique like Strassen's multiplication to reduce this exponent down a little bit from 3. But in addition, you are computing n approximations, which means that each time you are going to do one more multiplication, and so your overall cost is n times n cubed, which is going to be O of n power 4. Right? So that's an expensive algorithm. So the next thing what we do is we sort of talk about, okay, is there anything better that we can do? Okay? So the first thing that we do is we say, okay, this was the matrix we had, right? And the way we computed so far is that we, instead of doing, so let's take the case, instead of computing something like this, we ended up computing, right? Because we said we compute L to the power I, which means that we are doing these multiplications, we are associating these multiplications to the left, right? And that is leading us to this complexity of n to the power 4. What if we do the association the other way, right? So we do L times Z, right? So if you do L times Z, that's only n squared time, because you have an n by n matrix multiplied by n by 1 matrix, right? So when you have n by n, which is multiplied by n by 1, right? So that takes O of n squared time to yield n by 1 matrix, right? So when we do this, we have spent n squared time and we still have only n by 1 matrix. So which means that each of these multiplications is going to take only n squared time, right? So this is one of the instances of the example that we had in the chain matrix multiplication dynamic programming example, right? So where we said, okay, if you, depending on how you bracket your matrix multiplication, you can end up with one order of evaluation being much more expensive than the other. And so what we see here is that the way we ordered it in the previous slide was more expensive, but if we order it this way, then we get something more economical, because each multiplication now only takes n squared time, and still there are the same n multiplications. So you have n times n squared, which is the overall time reduced to n cubed. Okay? So then you want to further improve, then you can say, well, if I have a dense graph, right, which means that the number of edges is of the order of n squared, then I may not be able to do better, right? Because in general, I need to consider, in this, I need to consider all of my neighbors. If I have O of n neighbors, right? If each vertex has O of n neighbors, then this cannot be computed in faster than O of n. But if you have a sparse graph, which is typically most graphs that we deal with are sparse, in those graphs, the set of neighbors, right, can be much smaller than the much smaller than n. And in fact, if you look at this min equation, it actually goes through only all of the edges, right? So you only have to consider all of the edges in the graph. You don't have to do O of n square work for each of those multiplications. Instead, what you do is you only spend time proportional to the number of edges. Okay? So when you do that, now instead of having a O of n cube algorithm, you have O of n times E algorithm, right? So which gives you this complexity. Okay, so you have an algorithm that is whose complexity is proportional to the product of the number of edges and number of vertices. Okay, so in fact, this is really what is called Bellman-Ford algorithm. Okay, and the interesting thing about this algorithm is that it's more general than Dijkstra's algorithm. Okay, so how is it more general? In Dijkstra's algorithm, we had to assume that there are no negative edge weights, right? So whereas here we didn't have to make any assumption, right? So far, what did we do? We said there is a matrix, you do matrix multiplication, and then we work through some ways of making the naive matrix multiplication based formulation. We figured out how to improve that. So there is no assumption that that there are no negative edge weights. Okay? As a result, this algorithm is more general, and naturally you are paying more, right? So in the case of Dijkstra, you had your cost was I guess it was an E log V. What was it? Something like that, right? So
E plus V log.
Okay, so E plus V log. Okay, so that's fine. So the point here is that you have a more expensive algorithm, but it is also more general, right? So in general, there is nothing, no better, more efficient algorithms are not known for graphs containing edges with negative weights. Okay. So again, what we have done is basically taken this iterative formulation and then, successively tried to, improve the efficiency and lo and behold, we ended up with this Bellman and Ford algorithm. So now, obviously, can we do? The question is, can we do even better, right? So the reason why we are not doing better is because if you look at this particular equation, right? So again, remember, this is the ith approximation of the distance to vertex j. Okay, ith approximation to vertex j, and for that we are relying on I minus 1th approximation. So to get to j, we have to get to some k, and then in one edge go from k to j. Right. So this is the familiar equation we've been working with from the beginning, and on the right hand side we are using I minus 1th approximation in order to compute the ith approximation. Right. So what happens is that we may be spending a lot of time because we are computing a lot of, we are updating this, computing many approximations for dj, right? So in particular, we are computing n approximations, right? Because we are computing d1, d2, d3 up to dn, right? So we are computing n approximations. The question is, do we always have to do that? Right? Because can we do something better, right? So one of the ideas is that, so again, we are always using the same equation, right? So if, let's say, nothing on the right-hand side changes, then obviously the left-hand side is not going to change, right? So in particular, if the I minus 1th approximation happened to be the same as I minus 2 approximation, then this quantity will be exactly the same between the I minus 1 and the ith iterations, right? So what we can say is that, well, if this hasn't changed in the last iteration, then I don't have to apply this equation again to update this. Okay? So this is sort of a simple dependency analysis, right? So I have an equation, and the question is whether I have to recompute the result of this equation, right? Or result of this expression, right? So I have this expression here, and if something has changed, then I have to recompute this expression. If nothing has changed, then I need not recompute, right? So the whole idea here is that, okay, can we avoid recomputation? And we can, and in fact, in practice, this can yield somewhat better performance on Bellman-Ford. But the problem is, if you want to try to show the asymptotic complexity, you won't be able to show that the number of iterations actually will always reduce, right? So the point is that in the worst case, even though you are trying to avoid needless recomputation, there may be situations where it is required to make those recomputations, and you cannot bound and say, no, you don't need that many recomputations. And as a result, the technique, even though it is useful, it doesn't really result in the performance being improved. So, but we can try another technique, right? So the other point is that why not we wait, right? So let's take this example, right? So we are trying to say that in order to get the lowest cost v, I need to have computed the lowest cost to u, and then in one edge from u to v, I'm going to, update the cost to go to v, right? So the way the equation works is that it keeps updating dj based on dk, right? And what if the dk value hasn't, converged, right? Then you're using this equation to update dj many times, okay? What if you said I could schedule these updates in such a way that I will wait for u's shortest path to finalize, right? So once I know that I've already computed the shortest path to u, only then I will try to update the shortest path to v. Okay? So this is again another way of scheduling these, reevaluation of, right? So again and again we are reevaluating the right-hand side, right? And this is another way to reschedule, reorder how we schedule this evaluation. And if we do that, then we could potentially avoid repeatedly making these updates many times, okay? And instead, what you can do is, let's say, so what we are saying here is that V has, let's say, k neighbors, right? If V has k neighbors, what we are trying to say is that we are going to do this propagation from a neighbor to the vertex V only once per edge, right? Because we are going to wait until the cost of this shortest path to u stabilizes, then we propagate the cost from u to v by saying dv equals du plus luv, right? And of course there will be a min. Let's call this u1, u2, uk, right? So then what we are saying here is right? So if there are only k neighbors, then that equation basically looks like this, right? So you go to any of its neighbors, and then from its neighbor go to v, right? So if we blindly do the fixed point iteration, then we evaluate this whole min expression n times, right? Once for each iteration, right? So so now instead what we are going to try to do is to say, I'm not going to consider this, okay, until such time U1's cost has stabilized. Similarly, until U2's cost has stabilized and so on, okay? So essentially what we are going to do is we are going to propagate the contribution of the path to U1 only once on this edge, and then U2 once along this edge, and UK once along this edge, right? What that means is that the number of times we are going to update is going to be bounded by the total number of edges, right? Because basically what we are saying is that we are going to propagate this once per edge, right? So essentially what happens is that the total time that we spend is going to be just, order of E times. So we are going to update only order of E times. Okay? Yeah?
Is this like an amortized analysis or
It's not really an amortized analysis, right?
or you are just changing the algorithm?
So I guess, when you say amortized analysis, what that means is that, sometimes some steps take more time than other steps, but then if I average over all the steps, then the cost is such and such. This is not amortization, more like counting, right? I'm saying that the cost is going to be, the update, instead of thinking about the update in terms of this equation, I'm instead going to attribute the propagation cost to the edges, right? And therefore, since there are only, E edges, right? So what we are saying is that you can propagate only once through each edge, because, again, the reason for that is because only after the cost of U1 stabilizes, I'm going to push its propagation to E, right? So therefore, I can do this only once, right? So if there are E edges, then I can do the propagation E times, okay? Now, of course, I haven't said how long it takes, because there may be some computation that I may have to perform in order to figure out that the cost of V has stabilized. Okay, and so it's not that the total cost is O of E, right? Because I do have to do some work to be sure that the cost of U1 has stabilized. Yeah.
So does the graph has to be acyclic, or doesn't this affect it?
No, it doesn't affect anything, right? Because, see, the reason why you're thinking about cyclic is, again, in your mind, it seems hard to think that how will I know that U1's cost has stabilized, right? If there's a cycle, it seems to you that perhaps, it wouldn't stabilize. Or
I mean, after updating V,
yeah,
maybe I will have to update again.
Right. So so the point is that we have decoupled the two tasks, right? How do you determine that the cost of U has stabilized, right? That's still, we haven't solved that problem, right? Now, if you assume magically that you have a technique for determining when the cost of U1 has stabilized, right? And let's say, and if that is, and only after that you're going to update V, well, okay, then you only need this many updates, right? The reason why in the previous times you had to do more updates is because you didn't make that assumption, right? You didn't make the assumption that U1's cost had stabilized, right? So in the previous algorithm, you could very well have what you said, which is U1 makes a contribution to V, and somehow V makes a contribution to U1, and so on, right?
So this will not happen, that after I update V, I will not need to update the source?
No.
No.
What I'm saying is that you are, in this algorithm, someone is assuring me that the cost of U1 has stabilized. Only after that I do this propagation, right? So the question that you're asking is, well, what if that person was wrong? Well, I don't know what to do then, right? So I make my algorithm based on that assumption.
I'm not saying that. I'm saying that after I update V, maybe I will need to update.
No, that means your previous assertion that U1's cost has stabilized is wrong, right?
You will not need to update.
That's all I'm saying. I'm not saying that it is obvious how to know this, right? I'm not saying that. I'm saying that if you assume that you know when this cost is stabilized, and only after that you're going to do this, then you can do with O of E updates. That's all I'm saying. Okay? So now let's come to the second part, which is how do we know when this cost has stabilized? Okay? So now, if all the weights are non-negative, we can in fact determine when the costs have stabilized. Okay? So let's make an observation, right? If the edge weights are all non-negative, okay, so there must be at least R vertices with shortest path from the source S uses R or fewer edges. Okay, so you can sort of understand this maybe if you work backwards or maybe if you work forwards, whatever, right? Because what happens is that if you work forwards, obviously after one step, right, you have computed the shortest path to at least one of the neighbors of S, correct? Because whichever has the lowest weight edge, right? S has let's say W1 and W2, right? Let's say this cost is 2, this cost is 3, and let's say S doesn't have any other neighbors, right? So after one step, you know for sure that W1 is the closest neighbor, right? So once you have computed the closest neighbor, it must have either the next closest neighbor, right, should be somewhere there, right? It can't be here, right? It can't be here because, you know, no, it can be here, I'm sorry. So the point is that it has to be at a distance of 2 at most, right? So, or you can start at the end, right? All paths are of length less than n, right? And therefore, let's consider the path that the last computed shortest path, which will be the, you know, the node that is at the farthest distance from the source node in the graph, right? Because if you look at
that should be at least n minus 1.
right. So that let's look at how in terms of farthest in terms of the number of edges, right? So at most that can be n, right? So in the previous iteration, right, you must have computed something that is before that, okay? So if you think through that carefully, you'll realize that if after k steps, right, you look at the costs that you have computed so far, right, then everything below k, right, where k is the number of steps that you have carried through, those should have stabilized. Okay? So this is in fact the crux of Dijkstra's algorithm, right? Because what Dijkstra does is it has this, you know, heap that keeps track of the distances that you have computed so far, and it always picks up, and in the ith iteration, it picks the lowest cost at that point. And if you look at the overall cost, it is the ith lowest because the I minus 1 entries have already been removed from the heap, right? So in the Dijkstra's algorithm, in fact, relies on this property. And by relying on this property, it says, okay, I have already computed the shortest path to that node, and that's why after that, only, so if you remember, Dijkstra doesn't update every time a node's cost changes, right? Instead, it only updates when you dequeue that particular entry, right? So when you dequeue that entry, that means, you know, you have gone through k iterations, you have computed the kth smallest distance, and then each neighbors are updated. Okay, and it's exactly, you know, what we are doing here. That is waiting. You know, we don't propagate from U1 to V until we know that you have computed the lowest distance to U1. Okay, so that's exactly what Dijkstra's algorithm is doing. Just making sure that this updates from U to V are scheduled so that they happen only after, you know, the cost of U is known to have stabilized. Okay, so now that's single source shortest path, right? So we have this Dijkstra's algorithm, which again, basically what we did was we started with this iterative formulation and then said, okay, how can I, improve the efficiency of, each iterative step, and you keep improving, and then you get this Dijkstra's algorithm. So now let's look at so far we looked at the single source shortest paths, right? So one case, Dijkstra's, where none of the edges have negative weights, and Bellman-Ford, where edges can have negative weights. But of course, the problem of shortest path itself has no meaning if you have negative cycles, right? So we will never consider graphs with negative cycles when we talk about shortest path, right? So let's not worry about that. But you can have individual negative edges, okay? So in that case, you have Bellman-Ford, which can deal with edge weights that are negative, okay? So now let's look at the other case where you are trying to compute all paths shortest path, okay? And once again, we have this equation which says that in order to go from U to V, you will first go to a W, and then there is an edge from W to V, right? So this is the same equation that we had before, and we use the same equation for single source shortest path, except that the source was implicit the last time, so we just called it dV, right? Now, because we are considering all paths, then we have to make the source as well as destination explicit parameters in that equation. Okay, so now in order to compute this, right? So DUV depends on DUW, right? But it doesn't depend upon DXY if X is not equal to U, right? So you're going to start from U and go to V. In order to do that, you'll go through a vertex W. But you're not going to, if you're going to start from U, you're not going to start from some unrelated vertex X. So we don't have to worry about that. What that means is that the so if you think about this, right? So the one obvious way to do this is to say, okay, let me fix U, right? And then do this, right? So this I can do, and this is just a single source shortest path starting from U, right? So you can certainly do this, fairly obvious. Just very obvious thing of running SSP n times, one starting from each vertex, right? So that is certainly possible, okay? And that gives you, EV log V if you could use Dijkstra's, that is if you have no negative weight edges, right? So remember that, I guess, yeah, so we assume that the cost of Dijkstra's is E log V, and so you have to run it V times, starting from each vertex, so it gets EV log. So this is sort of a very, very brain dead way of doing it, right? So of course it'll seem stupid, but then as we know, there aren't particularly better solutions. So this is actually one of the competitive solutions to the all pass problem. Okay, so let's try a second formulation, okay, where instead of letting the intermediate vertex be one edge from V, right? So in the previous, so we are taking this, so if we go here, right? So far, we were working with this equation, right? So we were working the shortest path, single source shortest paths were all worked from this equation. The viewing the all pairs shortest path as n instances of single source shortest path was using this equation. Now we are going to use this third form where W is an arbitrary intermediate vertex, right? Whereas here W is adjacent to V, right? It's just a predecessor of V in the path. Whereas here, W is just some random intermediate vertex. Okay, so now